Okay, good afternoon, everyone. So my talk today is a little bit different with another one. Just looking for more head-dead stuff. I hope you don't be drowsy with this one. Okay, have you heard that? I think from fluid mechanics, one of the very challenging topics. And today I will talking about how to model it and how to apply it in the hydraulic engineering. So here is the content of my talk. Okay, I'm used to look at that one. Okay, so I will go through the one. First, I will introduce you what is about turbulent and some characteristic. And particular now, I'm trying to explain you the factor geometry, the very specific area from mathematics to explain some phenomena in hydraulic engineering. And I'm going to show you we are going to calculate the turbulent and compare with the result and some conclusions. So every people know it's Navier-Stokes equation here, right? That is Navier-Stokes equation. That is okay. That is Navier-Stokes equation. It's the middle 1800s. That is the fundamental of the study of fluid mechanics. So it's still millennium problem. That means if people can solve that problem, you can get $1 million. You know, it's still nonlinear and very challenging problem now. So to solve that problem, usually we have three ways, right? I told you that it's theoretically still millennium problem. And then, in 2015, it's a very, the guy, Thinh Nguyen, a very genius mathematician. It is 24 years old, already full professor at the UCLA. And he got on, Field Prize medal on honors, prize from mathematics. And he got, that is $3 million for the breaking through prize. That from the Zuckerberg and Yuri Miller. But that is not solving fully theoretical Navier-Stokes equation. That's only for wave propagation. What does it mean? That's still a wave from boundary layer. Okay, that is only on the surface wave. It is still missing the boundary layer. Okay, so another one is long times ago, people do experiment. But as you know, that is very, very limited and expensive. And the only way we can consider how to solve Navier-Stokes equation numerically. And that basically we call it CFD. Okay. So how now I talk to you, mention you some characteristics of the turbulent. Okay. I heard from Professor Bay, likely today I focus more at the lecture, okay, not like fully research result. And you can see, we mention later some very challenging numerical simulation later on. So the first one, talking about a turbulent flow, it's talking about high Reynolds number, okay, that very high Reynolds number. That is the relationship between the initial force and vertical force, okay? They're talking about a high Reynolds number. And the next one is turbulent and chaotic. Okay, you see the motion, it's randomly, okay? The next one, diffusivity. That is the transfer from momentum, from heat, from mass transfer. If high Reynolds number, but not diffusive, it's not turbulent. Okay. So another one is dissipation. So how about the energy dissipate from large scale to a small scale and dissipate? Okay. And the next one is rotation and vortex. You see here, the smoke or the foggy flow around that here. You see that is the vortices. And the next one is very challenging for simulation, that is coherent structure. Turbulent flow, there are two characters. The first one, it randomly, you see it chaotic. But that is still easy, because you can simulate it by the Gaussian distribution. Another one is very difficult, that they call it the order motion, that the motion but coherent, okay? And how about that later? I will show you. I use the factor geometry to explain how about the coherent rolling of the vortex structure. And for that, capture that properties, you need to deal with two scale, a small scale, a large scale. And for that, we need large simulation that I will tell you later. Okay. Have you heard about factor geometry? Okay, that is very beautiful from mathematics. So if you have the tree here, okay, also I told you from small scale, you know the pro motion, right? Look like that. But you cut off the small piece, small window, you will see the geometry will they call this cell similar. Again, very cell similarity geometry again, okay? You see the snowflake, the small one, you go down smaller scale, you will see the same geometry. You see here the tree here, you cut off right here, or you cut off small big branch here, you will see this almost the same geometry repeated again. That is called the factor geometry. You see that picture, it's very beautiful from river network in China. You see it look like from here, you cut here, or you go down small scale here. The geometry is repeated again, very similar. Okay. Here is how about that is using the factor geometry to explain how about the meandering cell meander. Okay. For that simulation, I believe I read about 4 publications, 2 from Nature and 2 from Science. Very challenging, but very, initial idea to use the factor geometry for the, to study for the river network, river morphology. Look at that picture. If I studied, I don't know, Professor Bockwick, he gave me last week. You see that one took from NASA, that from the, the morphology of the river in the Siberia. It's beautiful, but the same, that is factor. Okay. Here, it is, the alluvial channel, that is also factor. You cut here, or you cut right, it's more big here. Geometry is cell similar again. That is the beautiful of the nature. So here, you see that in another one, it's Brighter River in Iceland. See, the big one. We cut a window here, cut smaller one here. You see the same geometry repeat again. Okay, sum up that, just show you the very nice picture from the idea from factor. And now, it's not that one. Okay, here. Now I'm going to use that one to tell you what about the vortex in turbulent stretching. That the first one. Have you ever met the, to bake the cake at flour? You roll this flour for that one, and you roll it, and it gets tinier to longer, right? And then that roll it again. That is the vortex stretching and roll from large scale to a small scale. Okay? That is the idea from factor geometry. Okay. See here, see that picture. From here, you inject another small perpendicular with that one. You will see. First one, I have 2 vortices. two vortices here. And then, very last one, the second one you see build up 4 vortices. And you see the scale is smaller. Okay, that is the idea. The energy dissipate from large scale to small scale. And again, next one we have here 6 vortices. And gets smaller, and now it's energy dissipated. Okay, that is the idea from vortice, structure. So, to simulate the turbulent structure is very challenging, because we need to capture both scale. From the small scale here, they call it micro scale, cosmograph scale, and another one is large scale. If you relate ratio between 2 scale, okay, look at that one. Remember, the Reynolds number in the nature is usually million. Okay, million. For example, here I just take one example, smaller one, 10,000. 10,000, you see here. If I want to capture for both scale, my grid cell should be like 1 meter, another one is 1 millimeter. Okay, that only for Reynolds number. And 1 million, you will see, 3 more order larger. It is very, very challenging to capture for both scale. Even for time scale, also the same problem. Okay, the one is 1 hour, another one with second. That is very difficult. Okay. So to do that, there are 3 ways. The first one is usually overwhelming from up to now for the computer facility. We only do the mathematical simulation. It means totally taking the Navier-Stokes equation, solving numerically fully. Everything is keep the same. And then for that, up to now for supercomputer, we can solve the Reynolds number up to 5,000, 8,000, no more larger. Okay, but I told you in the nature, the Reynolds number is million. So that's very difficult. The next one is we use the filter. We simulate the large scale and sub-grid scale. We model it. And one more, very popular, people use. So up to now, like 30, 50 years still using this one, they call it Reynolds average Navier-Stokes equation. It means we are going to model the whole Navier-Stokes equation. Average, okay, they call it Reynolds average Navier-Stokes equation. So that it currently, it shows you 3 methods to simulate or to calculate the turbulent structure. So I might skip it. The first one, I just emphasize here. If student, you are going to take the class talking about Reynolds average Navier-Stokes equation, don't be confused that it's not time average. Okay, remember it's not time average. Many students confuse it. Okay, that is Reynolds decomposition. It means you decompose your true value in the average value and another one fluctuating, no matter what. That is the most beautiful of mathematics, they can say that. But in reality, people confuse with that one. That is the time average. But that is not the time average. That you have a 1,000 ensemble, and then you took that average. That's the time still stay here, right? That they call it URAN, that is unsteady Reynolds average Navier-Stokes equation. So remember that it is different. So okay, I skip it because after the average, you got this term. It substitute in the Navier-Stokes equation, you will see you got the new term here, new term here, and how to do with that. That is the reason why you need to model this term. So their term they call it Reynolds states. Okay, so and the basic idea is you is that Bussinet approximation. The basic is based on the laminar flow. Look at that here. That is, you remember that part for me, that is from laminar. If I use me here, that is for the molecular, right? That is, now the same here, I just substitute here, that is turbulent viscosity. And that is the idea from laminar flow. And then for this approximation, we stuck here kinetic energy. We stuck here with μT. That is the additive viscosity, right? So we need to model that one. Now I'm going to introduce you the number of the time. And then I'm going to compare that using the simulation and see what's going on. The first one, very popular, that is two equation. Two equation, what does it mean? It means you simulate the term using only two equations. They call it kinetic energy and energy dissipation, the key and epsilon. The first one, that you see here, that is long time ago, almost 40 years ago, using at the Empirical College in London. And one of my professor in Karlsruhe, Rodi, he's working with the group. He has working together that. And this model, still apply up today, okay? So here, that is, I show here, kinetic energy equation and dissipation equation, okay? That is the call it standard key epsilon model, very simple one, okay? So, but that working only for high Reynolds number, for the low Reynolds number, near to the boundary, near to the wall, not working. So we need to use some technique, they call it damping function. That is the one we deal with one damping function near to the wall. And for that, I just show you how to set up the model. Okay, you have the domain, you have inlet, you have outlet, you have the wall, you have the surface. Okay, you need to deal that with hydraulic engineering or any other. Okay, so first one, inlet. How you set it up? Here is the condition at the inlet. Okay, you need to provide kinetic energy dissipation. Look at that, complicated, but very simple. If you know the particular based on the turbulent intensity, and that here is L, they call it characteristic length. Many students confuse this one, characteristic length, that up to your modeling. For example, I model the flow around the cylinder like that. My characteristic length should be the diameter of the cylinder. I'm going to simulate the river. My characteristic length is actually, they call it hydraulic radius, but not easy one, water depth, right? So you flow around the building, what is your characteristic length? The height of the building. That it depends on and then you set it up easily. So here is some more specific, I might skip it because detail. And near to the wall, we need to use the wall function. That is logarithmic velocity profile, okay? Here it logarithmic. Actually, the graph here show you logarithm because that you should see it very linear here, but that actually, if you y plot only, you see the logarithm profile. Okay, here, logarithm profile. And near to the wall is linear. Here, linear. That is the near to the wall function using the velocity, the logarithmic velocity profile. And here, provide you here. And if you deal with the roughnet, you have some specific formula that is the roughnet height. Okay. So for the outlet or symmetry, you can use that it is Neumann boundary condition. Particular for hydraulic engineering, you need to deal with the free surface. It's very challenging because that is the way surface. So you use at the moving grid. That means you remove the grid moving with your simulation. Another one you can do with volume of fluid. You do with two-phase flow, the air and the water. You check in the concentration between two air and water. You capture the free surface. So I'm not going into detail with that, but I just tell you what the key epsilon model can do is that the advantage is easy, okay? And the prediction is some, convert easily set up, but that is inherent a lot of disadvantage. For the flow with the separation, flow with the strongly curvature or swirl, key epsilon model gave up. Okay, and what we do now, we need to move a little bit more. And then the next, for example, here I show you here. Here the pi, okay, here the pi, I made a symmetry here. For comparison, you can see here that the observation here is simulation using key epsilon model. You see how much different. Separation flow here, using key epsilon model, it over predicted, okay? And capture here, the core flow is different here. A lot of differences between the numerical model and simulation and observation. So we need to move a little bit further. You use R and Z. Okay, the R and Z, the only thing different, we add in one more term here. That from renormalization growth, they add in R here. For the key epsilon model, epsilon is so simple. So they add one more term here. Okay, R is here. Let's here, improvement. Okay, not much improvement, but it improve a little bit here. For high stream curvature can capture more precise compared with key epsilon model. Some kind with the heat and mass transfer or transition flow, it's a little bit better, but still poor. Now we move a little bit more. They call it realizable key epsilon model. Realizable key epsilon model is the only different here. You remember? Here is key epsilon model. I use the CV constant. Realizable now, CV no longer constant. Let it move. Okay, and then okay, here it's realizable. Okay, let it CV no longer constant. CV in key epsilon model is 0.09, but now it lets it move with kinetic energy and dissipation. And see what is improvement. Here is the improvement. Okay, that is for the boundary layer. It's a little bit improvement, rotation, circulation, and strong stream curvature improvement, but still not enough. So we know with non-linear model. Okay, up to here you have a key epsilon model, and we add one more term here. That is third order and etc. Okay, and see what's going on. Here, that is equation. Here is quadratic. Okay, order, and then they call it. I'm not going to the formula here. Another one is the cubic. Okay, add quadratic term, another one, then and cubic term, another one. Okay, and next for key epsilon model is not enough. Now we see the Wincox apply another model. They call it key omega. Also belong to two equations. Okay, that is a long time ago. It is the time. It's about 30 years ago. Okay, and recently it's Mentor used the HAT key omega model. That's they call it the shear state transport model. Actually, that is very smart model. Combine key omega and key epsilon together. They use the function switch on off. Turn on where we need to turn on key omega, where we need to turn off. That is at AT. Now, another one is V2T also for the two equation model. So let's see here. Here the notation. You see here the flow, over a step. A step height is the same. The ratio of a step height is the same with a half of the height. Okay. So you see K epsilon V2F. INZ, K omega, realizable, K omega HHT, quadratic, that is nonlinear, and that is nonlinear. And here after 200 seconds, you see, very different. The same problem. Everything is the same, but the result is totally different. Okay? You see how much different if you use different model. Now, at the final step, when the solution is got converged. So we get here, it's very different. The only thing is nonlinear. It is very close result together. And all other, different. Simulation only very simple one, 2 dimension, the flow over step. I give you the idea how much different. So another one, you don't need any more model. You use fully the Reynolds state with 6 components. Okay, for it here Reynolds state. I already told you what is the Reynolds state here. Split into 5 components. The first one is that is production. Second one diffusion. Here is dissipation. That is here the turbulent pressure strain. Here omega is the rotation. Okay. Here you can model it. You can exact value. Here you can model it. Here you can have exact value. This one need to model. This one can have exact value. Okay. I skip this one. So on the formula here, I skip it. Okay, what is advantage fully Reynolds state model? You don't use any model. You saw truly the Reynolds average Navier-Stokes equation. You got more precise. But up to now, the simulation time is the same with last AD simulation. So it no longer, you use the model. But the same with another one is better, so you should use the better one. Okay, with last ID simulation. That is the next. That is, I remember at the beginning I showed you DNA, last ID simulation, and range. Here it is in between that. This is the one. The basic idea, you split the value into one is fluctuating, one is the mean value. The first one, you ran it different way. Now they use the filter. They use the filter out, you use the zip, you screen out the beam, right? And the small beam can go through the zip. The larger beam can stay upper. Right? It's at the large scale of the turbulence, you stay here, and small scale go through the zip. The zip look like the filter. Okay, this here the filter. Okay, so after you use the filter, you filter out the large scale and small scale go through. Small scale need to simulate. Okay, the large scale do indirectly simulation. That is the basic idea from last AD simulation. Okay, here. They have the filter, 3 filter. The first one they call it top hat. Another one is from Stanford University, they use that one. Another one here. Both here very difficult. It unreal. It rewind very only for research purpose. For the the application in the real world, it's not efficiency. So that's the first one. Actually, they call it top hat. It's using that based on the crystal. Okay, here is the crystal. Okay, it may look like the zip I told you. That is the crystal. The last one keep it, the small one let through. Okay, the small one they call it subcrystal scale. Okay, after that, substitute in Navier-Stokes equation, apply here, and the end, you get this one. This here, they call it, it's very similar to Raynaud state. They call it sub-Ricci scale state. And for that, we split into three terms. Leonard states, cross state, and less Raynaud state. That is this one. And we are going to deal with that one. It looks like very similar to turbulent Raynaud state here. Okay, and to simulate that one, we have the idea is the same with the Raynaud state. We use here, it looks like one. Very similar with the Raynaud state. This guy, we need to model that. Okay, this guy, we need to model that. And so they have many, many models. Okay, for example, the first one, equal, they call the, don't use any equation. They call the same with missing length in Raynaud state, Raynaud average. We use one model, one equation, like here. The same with one equation in Raynaud state, Raynaud average, Navier-Stokes equation, etc. Okay, so here is set up the boundary condition. The only thing very challenging with Raynaud average Navier-Stokes equation, the Y flood is between 30 to 300. The Y flood less than 1. Y flood show you the phi, the density of the mesh near to the wall, okay, to capture the boundary layer. That is very fine grade. And the inflow is inlet, very challenging, okay, very challenging. Okay, the outlet here, I might skip it. How many times I still have, sir? Okay. Over? Oh, okay. So now I show you some truly application. This is the observation. Okay, the flow over step here from my lab in Rivet lab in Germany, and they do a lot of simulation here. And I show you now it's just some more picture. Okay, here I compare with RAN model and LES. You can see how much different. The LES gives a very good one. Here, the LED is the black one, the blue one, and that is RAN is the black one. You see how much different. Okay, compare with here is observation. LED is capture very good. And another one here is experiment from at NU, and here is some cross section here. Remember that? And we here compare here the secondary flow. You see here it RAN, here it less. RAN it fell near to the wall, but LES still capture very good near to the wall. Okay, it's the same idea that. Now I show you some more movie. Here is the flow around the cubic, and here you the realizable K epsilon. Here it lost at the simulation. You will see here. You see how much difference between two models. Here is the vortex. You see that the vortex here from realizable. Here is the less. You see, it's totally different. Very much different. Here, the vortex is more, here it less vortices. Okay, next one. Compare that with the simulation here, you will see let it capture the flow after the block. It's more precise here. And here, another movie. The flow along around the cylinder. The upper one is the less, the lower the K epsilon model. You see, it's very much different. Right? I have a lot of movie here. I skip it. Another one is the same idea, but I use different model. Right? Realizable, INC, and less. You see, three models show a lot of different. You see, the same problem, but you apply different turbulent model, you get totally different result. Okay, very interesting. Keep in mind that when you start to do a turbulent model, you need to know, okay, which model it fits with your simulation. And here I capture the free surface. Using K epsilon, here it lasts at the simulation. You see how much different here. The more challenging it captures the free surface, the flow up over a step. Here, you see that it less, and that is the K epsilon model. Very, it's like unsteady situation. And here it, steer in the tank. You see that it's the voltage structure. And now I show you the last one, very precise, very simple one. The flow in the cube, but over the cyclic, the flow outside here. People said the flow just stayed here, no secondary flow, right? And you keep in mind, you think, okay, the flow stayed here. But actually, you do very precise, you will see here. That is secondary flow. Where the cut, you made a cut here, you see the flow data. But we said, okay, the flow data, never you can see the secondary flow. But truly you see that. That is, I run it with a red numerical simulation with very low Reynolds number. Okay? So, here I just summarize you how to use that one. Okay. Here the curve show you how the facility of the high performance computing, CPU time, a number of the grid size, and you see here that it for the 0-10, what I show you there, ENet still, how many cells you hear, that it requires, very large, strong computer, led in the between here, and then it going down here. Okay. Okay, here's my conclusion. Okay, remember, if you do something, you don't need to challenge in your turbulent structure. Two equations, K epsilon model, still alive. Like you do in river. Okay, or you large scale, 5 kilometers, 10 kilometers of the river. Who will provide you the data to validate the turbulent structure? No way, right? It no sense to do that way. But you want to capture a smaller structure, like around the hydraulic structure or somewhere small scale. You might do with large eddy simulation. DNS still theoretically still low Reynolds number. Okay. Thank you very much. Sorry, I just burned.